Okay, our today's speaker is Evgeny Golikov, who'll give a talk about the progress of infinitely wide, neural networks, and in particular, neural tangent kernels. This is one of the ongoing trends in modern theoretical machine learning, and the topic is quite unfamiliar for us. So hopefully, we'll get more familiar with it after your talk. So Evgeny, please.
Thank you. So what are the goals? So typically, neural networks are the objects that are hard to study theoretically. There are several reasons for it. The first reason is that they have non-convex optimization landscape and a non-deterministic training procedure. That's why it is hard to get any optimization guarantees generally. And also, it is known that there exist purely generalizing minima, and they can be constructed. And for this reason, it is hard to get any non-vacuous generalization guarantees if we do not take training dynamics into account, which is complicated because of the first 2 points.
I'm sorry, probably you meant poorly generalizing minima.
Poorly, sorry.
Okay.
It's a typo, of course. Uh, so what can we do? So we can come up with some theoretically tractable proxy model and try to relate this proxy model to a real network. So generally, of course, neural network training process have some hyperparameters. They are learning rate, batch size, depth, width, and we can hope that if we take some limits with respect to some of these hyperparameters, we'll simplify our model. For example, if we take a limit of 0 learning rate, then we obtain a continuous time gradient descent instead of discrete one. If we take an infinite batch size, then we can say that it is a deterministic gradient descent, not stochastic one. If you have an infinite depth, then I will argue that probably it should be something like ODE-net. If you, because ResNet is a type of neural networks with finite depths, and if you take an infinite depth, it's kind of should be ODE-net. And in today's talk, we'll consider the case when we take a limit of infinite widths. It turns out that there are multiple infinite width limits. The first one, the most widely known, is the constant Ntk limit, which is due to Jacob and co-authors. And there are also maybe not very popular, but still there is a mean field limit, and there are multiple pioneering works dealing with it. What is the difference? Why do we have several infinite width limits? Turns out that the difference, the cause of the difference is the hyperparameter scaling with widths. So for these two limits, hyperparameters are scaled with width differently, and that's why the limits are different. So the questions are the following. So what are the properties of these limits? And which of these limits is a better proxy for a finite width network? If we want to substitute a finite width network with a simpler model, what would be the better model, the better proxy? And can we have any other infinite width limits? We start with discussing the Ntk limit. Um, Consider a model, a general model F with input X and weight theta. And we aim to minimize a loss L at theta with a gradient descent, with a continuous time gradient descent. So here we have dynamics and initialization, theta 0. If we multiply this dynamics by nabla F, just do the following, then we'll get the dynamics in a function space, not in the weight space, but in a model space. And this dynamics is driven by some kernel, which is called a neural tangent kernel. A neural tangent kernel at 2 points, x prime and x, is a scalar product between the gradients of the model at 2 points, x prime and x, and the gradients is with respect to weights. So it's kind of gradient similarity. Um, what should we note here? In the second dynamics, in the dynamics in the model space, uh, all of the weights are now hidden. They are hidden in the tangent kernel. So there are no weights here anymore. And this allows us actually to take in a limit of infinite weights, because if you have dynamics in the parameter space, then you cannot take a limit, because uh, because you alter the number of equations if you take a limit. But here, if you deal with functions with model itself, then you can take a limit. Uh, but so what happened? So the second thing we should note is that Ntk is generally stochastic and it evolves with time.
Evgeny, may I ask a question here?
Okay, yes.
The second equation. So you start with the f point of x prime.
Mm-hmm.
Why you end up with a kernel here? So where's x in your left-hand part?
Whereas x in the left-hand part,
Yeah.
because in the first equation there was x, and we have expectation over x and y. It's expectation over training data, x and a sample from training data.
Okay.
And there you still have this x, which is a sample
And
from.
you compute expectation with respect to this x, the expectation of loss gradient times kernel, right?
Yes, yes.
Mm-hmm. Okay, thanks.
Uh, the second thing that we have to note is that Ndk is generally stochastic and evolves with time. It is stochastic because weights are stochastic, weights are initialized randomly, and it evolves with time because your weights evolve with time. That's why by the first equation was how to say consistent, I think, because we can integrate it.
I have a question.
Yeah.
So I'm not completely get what is conceptual difference
Mhm.
between the first and the second equation. So can you elaborate more, because it's a kind of new topic for me and I'm not really get it.
Conceptual difference. The first equation is the dynamics on parameter space. Yes.
Yeah.
And the
Yeah.
second one is the dynamics in the function space.
Uh,
Uh,
can you explain a little bit more how these dynamics in functional space should work, or something like that? I'm not completely understand it.
how should work on what?
So I can say that I understand how training works in parameter space, but
Mm-hmm.
when we kind of switch our space to functional space, I
Mm-hmm.
am not completely understand how it works in function space.
How does it work in function space? What do you mean? How does it work? Do you mean some intuition on
Yeah,
what
yeah,
the kind of
yeah.
as
What we are doing kind of conceptually here.
conceptually, your kernel can be seen as an operator that maps your loss gradient with respect to model output to model increment at some particular point x prime. You have a particular point x prime. You want to compute how that the model output would change on this x prime, and your kernel says how does this, and this kernel maps loss gradient at, I think, no, just loss gradient at some point x to an increment of the model at other point x prime.
Okay.
So this means
Okay.
how your output changes, your output at the particular input x prime, how the output changes with training dynamics. So that's why it's written here that this is the gradient of your output at x prime times the dynamics of your weights. So this product gives you exactly the evolution of the output at x prime during training process.
Thank you. Thank you. Now it's much better. Thank you.
Yes, I'll continue then. So the first equation is self-consistent because you can integrate this equation. Your gradient descent, what it does, it integrates the equation. However, the second one is not, I would say, complete, I think, because in order to integrate the dynamics, you have to specify your kernel. And given only this equation itself, the kernel is not specified. So by switching from parameter space to model space, we have lost some information. That's why the second dynamics cannot be integrated. It can be integrated if we specify the kernel somehow. So if this KT is known, but it is not known. Nevertheless, it turns out that in some specific parameterization, in the limit of infinite widths, this kernel, KT, is deterministic and constant and can be computed. I will elaborate this point. So first, consider a model with L hidden layers of width D in default parameterization. Sometimes it's called standard, but okay, the default parameterization. The training process is a gradient descent, and we initialize our weights using a key initialization scheme. I mean, the initialization is zero-centered, and variances are inverse proportional to the number of input neurons. So we have the same number of input neurons on all of the hidden layers. That's why the first layer initialized is like this, and all others are initialized like this. So let us switch to another kind of parameterization. It's called Ndk parametrization. Here we move the factors of d to the -1/2 to the definition of the model. And in this case, your weights are initialized independently on weights. So before we have initialized our weights that are inverse proportional to the square root of the number, one of the square root of the number of input units in each layer. And now we have moved this factor to the definition of the model. So the model at the initialization didn't change. However, the training process changed because we have somehow rescaled our weight space. And in this case, it turns out that the Ndk, the corresponding neural tension kernel, converges to a constant deterministic kernel, which is just an expectation of the kernel at the initialization.
Excuse me, what is L small in the initialization of theta in?
L small, it's not L small, it is I.
Why is it I?
It should be inversely proportional to the uh, uh, input size. I agree, but because we are interested in asymptotical behavior with respect to the weights, and the input size, the size of X, doesn't depend on D, without loss of generality, I can assume that it is just
Okay.
identity.
Thank you.
And the expectation of K0 with respect to what?
With respect to initialization,
Mm-hmm.
we do not have any stochasticity anymore. Just for the sake of illustration, let us consider the case of a single hidden layer. And we consider, so we have single hidden layer. So the A is the output weights, W the input weights, and so yes. And here are the dynamics for A and W. And one can see, we have just taken the gradients, that for each individual neuron, weight increments tend to 0 as weights go to infinity. This means that the weights do not evolve in the limit. However, uh, just by definition, one can compute the kernel, and it would turn out that just by the law of large numbers, the Ntk converges to some constant deterministic limit. Just, you can skip this calculation, but what you should pay attention for is these things. You have a d to the minus 1 factor and a sum over d terms, and that allows us to apply a law of large numbers. And that is why in the Ntk limit, each individual weight do not evolve. It just, so they do not evolve. However, you have some Ntk, which is context deterministic, and it drives the evolution of the model.
By what way it drives the evolution? If the way
By the way, as I have written there. So in the second dynamics, your KT converges to some constant deterministic limit, which can be computed. And the evolution is there. You can just integrate it.
So this means that although the weights do not change, the outputs of our model still changes, right?
Yes, right.
But how can this happen?
How can this happen?
Yeah.
Because your weights do not change. However, the number of the weights go to infinity.
But can we say that actually the weights do change, but they all have infinitely small changes?
Yes,
so the weights
like
almost do not change, but due to the fact that they have an infinitely large number of infinitely small changes, so the total model output changes.
Yes, I think that's correct way to think of this.
Good.
And that's why this phenomenon is called lazy training, because your weights do not change. Your model is lazy. However, it still fits the data. So it fits the data in a lazy way. So almost no changing of these fits weights. And what happens in default parameterization? If you parameterize your network standardly, here we do not have this factor of d to the 1 over square root of d. However, this factor is hidden in the initialization of weights.
Would you repeat, please? What is A?
A are output weights. So here's the definition: A weights of the output layer.
So we have two-layered neural network. The weights of the first layer are W's. The weights of the second layer are A's.
And since we do not have this factor, in this case, I have just, again, taken gradients. Weight increments do not go to 0 as weights go to infinity. So the default parameterization is not lazy in the limit. Default, yeah. And we can compute the kernel. And this kernel, as one can see, because we have just a sum without any normalization, the kernel diverges at initialization. That's why I have to just state that the Ndk parametrization conceptually differs from the standard one. Okay, let us consider a model with Ndk parametrization or with D. We should prove some convergence theorem, and there is a convergence theorem of Jacob and co-authors. And this theorem states that for sufficiently regular nonlinearity, your kernel indeed converges to an expectation of this kernel at initialization with respect to initialization weights, and your model converges to some, your model fd at time t converges to some model f infinity at time t. And this model is given as the following. So where k infinity can be computed. And at initialization, this model is a Gaussian process, which is kind of clear, I think. So the initial question is, okay,
Not really.
Not really, because,
Not really clear.
That it's a Gaussian process. Maybe it's not really clear. Okay, I can give you maybe some intuition why. Because your weights. So let us consider the last layer. All of your weights are Gaussian. So at the last layer, you have a sum of a Gaussian times something which is independent of this Gaussian. So you have a
Yeah,
sum
okay.
of because of the CLG.
Could you please summarize why do we need this new parameterization? So am I right that in the standard parameterization and in the Ntk parameterization, the models are the same actually, but if we want to speak about the neural network in Ntk terms, then we need this Ntk parameterization. Because in the standard parameterization, the kernel will go to the infinity, and we can't work with the infinity, or what? I'm sorry if the question is stupid, but like there are a lot of formulas here, and it's very difficult.
I think so. We need Ndk parameterization just to have a nice limit
For the kernel.
Yes, because if you have a default parameterization, then your kernel diverges, and it's not obvious what the limit model is. But
so am I right that if we think about like that we trained this model, like this neural network with infinite number of neurons, then actually the network in the standard parameterization and the network in the Ndk parameterization, they will be the same networks. But if we want to understand what is the shape of this like model in terms of the kernel, then we need Ndk parameterization in order to like have not infinite kernel.
what do you mean the same model? Do you mean the same dynamics?
I don't really understand
The same functions probably.
Yeah, something like this.
The same functions. The same functions are realizable, but the training process will differ because you
Could
have.
you like somehow simply explain why is it different? Not like not in the formulas. Like in the formulas, I understand that we have d goes to infinity, blah blah blah. But I don't understand it like
the
I
same
see-
for
I
me.
think-
I need a lot of pictures.
I
Like
need to-
I think that we
really,
can.
I'm really sorry for not having pictures at all. So, okay.
Sorry, I think I have one explanation. We can just consider central limit theorem. In a central limit theorem, we have a set of random variables, and in order to have a convergence to some standard normal distribution, we do a normalization. We take a sum of our random variables, and then we need somehow to normalize them to take a mean, divide by standard deviation, and in this way converge to some standard normal distribution. The same thing is here. So if you have just a sum of some random variables, and the number of terms goes to infinity, it would not converge to any standard distribution or standard process. You need just to normalize it in some way in order to have a convergence to something that doesn't depend on parameters.
But does it mean that if we like hypothetically train the model without Ndk parametrization with infinite number of neurons, it will not work at all, or what?
It will not work at all until you have this default initialization. So given this slide, pay attention on initialization of W. We initialize it with a standard normal distribution. If we did that with a normal distribution with variance inversely proportional to D, then everything would be fine. But if your weights are initialized with standard normal distribution, and now you have an infinitely large number of weights, so of course you will have a divergent kernel because you have a plus infinity or plus or minus infinities at the output of the first layer. So that is the problem. Everything is more or less fine until you have finite number of neurons. But if your number of neurons goes to infinity, you have to somehow normalize your weights. Otherwise, you will get plus or minus infinities as the output of the corresponding layer. So I think this is the reason why K0 diverges here. And if we change parameterization, so if we explicitly take into account the number of neurons, this is exactly Ntk parameterization, then everything is fine, and we do not go to infinities anymore, and our kernel converges to K0.
So the short answer is like we can't think about the infinite network in the standard parameterization at all.
No, that's not the case, but we cannot think of the kernel for infinite networks in the standard parameterization. So
but I mean, if we think about infinite network in the standard parameterization, then we need the initialization with like 0 weights.
Yep.
And it's like, it's stupid. It will not work at all.
No. It is not stupid. And this explains the phenomenon of lazy training. So when Evgeny tells that the weights almost do not change, they almost do not change because they're almost 0. And if the weights are almost 0,
weights are not almost 0 because they initialize like standard Gaussians. They just stand the way they are initialized. They increments.
But then we multiply by D in -1/2. So weight normalized goes to 0.
Weights normalized goes to 0, right? But this weight W, they do not go to 0. But if we have an infinitely large neural network, I would suspect, given at least my intuition on the loss landscape, that in this case there exists a global minimum of training loss in the very small neighborhood of the point where we initialized our weights. So I think this again can explain the phenomenon of lazy training.
Okay, I think we should go. Like, we should go.
Bye.
I'm sorry. I mean, it still is not like clear for me, but I will think about it after the talk.
May I ask one short question?
Yes.
So how does this initialization procedure compares to standard initialization procedures for fully connected layers?
So the standard procedure is given in this slide. The initialization is standard because the weights are initialized with zero mean and variance inversely proportional to the number of someone, sorry, Latin, to the number of input neurons. So that's standard. And the question was, how does default parameterization relates to this, the initialization that is typically used or for the Ndk?
Is it the same as an initialization you use as default in PyTorch, or is it different somehow in details?
Here I take normal, but so it's like, yes, it's like Hamming normal. It differs only in the constant factors because you have some gain factor, but this gain factor does not change the asymptotics.
Thank you.
You can say that it changed. I will switch on the light because someone has switched it off. Sorry, just a minute.
I have one more stupid question. Okay. So we now have infinitely many neurons, yes?
Right.
But we still have finite set of weights that we are initialize. It's kind of controversial for me.
No, they are not finite. Why finite?
Why not?
Because the number of your weights should be proportional to the number of neurons you're using. So of course we have an infinitely large number of weights as well.
Okay, yeah. Okay.
So please continue.
Okay. So as one can see, so we have a convergence theorem. With Ntk parametrization, your kernel converges to a deterministic limit, which is an expectation of the tangent kernel as the initialization with respect to initialization weights. And your model converges to a limit model, which is driven by this kernel f infinity, the limit model, and at the initialization, this model is the Gaussian process. It is not obvious what should be the limit model for the default parameterization, and does it exist at all? And if I have enough time, I will show it. What is the limit model should be for the default parameterization, actually. And I wouldn't have enough time, then you can see the preprint. Yeah, so, and it turns out that the Ndk limit is very convenient in getting some guarantees, optimization, generalization guarantees, because you have a very simple model driven by kernel. You can just integrate it if you know the kernel. For example, consider you have a trained data set of size n, which I call Sn, and I assume as square loss, and assume that the Gramian of the kernel, so I take a kernel that computes Gramian on the training data set, and I assume that it is positive definite. It's always not negative, it is semi-definite, positive semi-definite, but I assume that it is positive definite. And then it follows that your model converges to a global minimum, very simply. So you have an L2 regression. So it's just a gradient of the loss. And by bold Y, I will denote the vector of targets. And by bold Y, t, I will denote the vector of responses of the model at time t. And let lambda I vi be a set of eigenvalue eigenvector pairs for a Gramian. Then it is easy to derive that your um, your how to say your error on the data set, your square error, will evolve as follows. So
Mhm. Interesting. So we have exponential decays where
yes.
the coefficient is proportional to the eigenvalue.
Mm-hmm.
We have decays. So the rates of those decays are different with respect to different eigenvectors, right?
Mm-hmm. Right.
And the
Yes.
initial magnitude depends on the y hat 0. Okay, so this is our initial error,
Mm-hmm.
right? And then we
Right.
start exponentially minimizing this error along different directions with different speed. But in all cases, the speed is exponential.
Yes. Yes. And that means that first, the first conclusion is that your error decreased to zero. You just converge to global mean. And the
Can we
second,
guarantee that we do not have a zero eigenvalue here?
I have assumed that the Gramian is positive definite. That's why all of them are positive.
But
So
I would,
it's assumption, but
Uh,
in real
no,
case, we don't know.
uh, you can prove there is a theorem that if your if none of the two none of the two inputs in the training data set xi and xj are the same, so all of them are different, then uh, the Gramian is positive definite.
Okay, thank
we may also guarantee zero train error, right?
Mm-hmm.
Well,
Here we
maybe
go.
that's not surprising. We have a finite training set and the infinitely wide deep neural network. But anyway, that's interesting. And so this result is more or less clear. I would say obvious.
Not that obvious, but yes, this result is quite simple. And another conclusion from this result is that okay, so as you have mentioned, there is a sum, and each term in this sum decays exponentially with different speeds.
Mhm.
And so, how fast does this sum goes to zero? Uh, if for so those terms with large lambda I will decay faster.
Surely.
Yes, and if it turns out that for that those that terms with small lambda I that decay slower uh, have this term y y0 minus y times vi already small, so your initial error does not align with the corresponding eigenvector, uh, then you will converge. Then uh, this um, the slow convergence of the corresponding exponent is not that important. So maybe I have so um, if for large alpha this spectrum alignment, I would say, is also large, and for small alpha, the spectrum alignment is also small, this will mean that your error will converge fast. And uh, this statement can, so I would say it's normal projection. This can explain why training your network on random labels is slow, because so there is a plot on the left. The histogram is a histogram of norm of projection of your target vector on the eigenvectors. And we see that for real CFR labels, for first eigenvalues that are large, your prediction is large, and for last eigenvectors, eigenvalues which are small, the normal projection is also small. And so you have a normal projection and you have eigenvalues. And since they are aligned, this sum will converge to zero fast, and it is depicted on the right plot. And you have random labels. Normal projections and eigenvalues are not aligned. That is why even for small eigenvalues, normal projections are not very small. And that's why on random labels, your convergence is small. And in the worst case, when your targets are aligned with the eigenvector of the smallest eigenvalue, which is, then your convergence will be extremely small. It's slow.
So does it mean that in some sense, our model of deep neural network should be aligned with the data sets we would like to analyze?
Yes, and that's interesting because in some sense, our realistic data and our networks are fit to each other
Yeah,
well.
yeah.
And that's interesting phenomenon because we don't know why that's the case.
And again, then can you please remind what is responsible for the definition of Ntk? So it
Let's
depends
see.
on what in terms of neural network?
Mm, it depends on the network itself.
So this is a scalar product of the gradients of two inputs. I'm just trying to imagine what would be the situation when our data set is not aligned with our neural network model. And I still cannot imagine such situation.
So it means that so again, what does the kernel what does it do? It takes loss gradient with respect to model output and outputs a model increment at some point. What is the spectrum? So what are the eigenvectors? So is eigenvectors of the Ndk are such how to say that gradients of the loss that the kernel will map them to themselves
Itself, yeah.
with some coefficient. And okay, if we, what does it mean that the targets are not aligned? It means that
Well, I'm afraid we will not be able to come up with a clear geometrical intuition
yes.
Immediately. But I think that this is the question that should be thought over, because that's important.
I
It will
agree.
allow us to form some intuition, which will simplify the further understanding of the phenomena. But okay. So now we have at least hypothesized that deep neural networks can be not aligned with the data sets that we are trying to analyze. But this is not the case of real-world data sets, but we can at least imagine the existence of such extremely strange data for which deep neural networks are not suitable. So maybe this is this can be an answer why different alternatives to conventional neural networks do not work as well as they do on real-world data sets. For example, such as tensor networks, for example, which many people try to learn on real-world data sets, and the results were pretty poor. So maybe this was exactly because those tensor models were not aligned to our real data sets, unlike deep neural networks. So that's interesting, and this means that the current architectures of deep neural networks have some kind of inductive bias towards the problems that we try to solve using them.
But this is true only with respect to a particular optimization method. So if we do not, based on gradient descent, and use, say, a Newton type optimization algorithm, we are, at least theoretically, able to get a faster convergence in times of t. Agree?
Well, that's right.
Right.
But again, it may happen that even for Newton-like optimization methods, there are still some kind of theoretical guarantees that prevent us from too fast convergence, and that ensure that there can be such data sets, such problems, for which the corresponding model is not suitable, and the convergence is extremely slow. These are, of course, speculations, but at least from the result which Evgeny provided us, we can say that at least for gradient optimization method, such situation is possible. Okay, please continue.
I have a question. Has there been any work trying to relate the result we're seeing on the left plot with the lottery ticket hypothesis?
Wow, I haven't seen ones.
Like
Not
the well, the lottery ticket hypothesis roughly states that in neural networks at the initialization stage, right before any training, there is a subnetwork that kind of already somewhat starts doing the task you're after. It's already initialized at the right values, and you just sort of need to clear up the space around it. What people do, they train networks, they sparsify networks, and then only look at weights that are left, and then it turns out that you can so you can train sparse networks from scratch, but what you can do is you can sparsify networks, leave only those weights that are good after sparsification, and then revert those weights back into the initialization. Then such sparse network would be training okay. So why I am asking is because I think there might be a connection if there is a good neural network somewhere inside your big network that's waiting to be discovered. Maybe it is sort of responsible for this non-uniform distribution of this norm of projection, and it just sort of happens that there is someone who wins in this kind of lottery, right? You just ordered this norm of projections according to maybe not just wondering whether that might be due to that maybe this result, the fact that the data set is aligned to the net model we're having, is due to the fact that we have exponential number of subnetworks, and some of them happened to do a good job.
I think no, because there was a theorem on ICML that proved that for any data, you can you can construct a subnetwork that solves the problem, something like this. A theoretical results, I don't remember the authors, some authors from Israel, I think, from Hebrew University. So this result states that if the network is sufficiently large, then you can construct a subnetwork that solves your problem, and it is proven for arbitrary data, not for real data.
Okay.
Can we can we also say that since in our NTK setup the weight stays close to initialization, that it means that the whole networks when predicting something, the whole all the weights are taken into account, and not so we cannot, since all the weights are close to initialization, we cannot choose some small subnetwork. All the weights will play their part.
No, that's not obvious why. Maybe some are smaller than others. All of them are smaller, some are smaller than others. Something like this, I don't know.
Okay.
Please go
on. So yeah, so far we have two results. The first one is that a finite width model converges to a limit one, the result of Jacob. And the second one is that a limit model converges to a global minimum, the previous result of Aurora, let's say. The second one is the asymptotic convergence guarantee. I mean that the limit model converges to a global minimum. Can we say that a finite width model converges to a global minimum using these two results? This result is possible. You can have a non-asymptotic convergence guarantee. So the first result is by Dew and co-authors for two-layered networks with ReLU activations, and they basically say that given some failure probability delta for widths large enough, very large, proportional to the n, which is the number of training points to the 6, you can have an exponential convergence with probability not less than 1 minus delta. Essentially, they prove that, okay, your NTK for finite weights is stochastic and it evolves with time. It is not deterministic at all. However, for large enough nets, you can bound its evolution. So you can guarantee that it does not go far away from the initialization, from the expectation of the initialization. So your kernel is almost stable, and it gives you the bound, the convergence. There are some more sophisticated techniques that gives you n to the 4 bound, which is also too large. And you can have a similar guarantee with the spectrum alignment, not for convergence itself. Also, you can have some guarantees on generalization. Consider L1 loss and assume that your network at the initialization is 0. It is possible. And assume that your network converged to 0 loss in the training dataset already. And let f hat n be the final net. We want to bound the loss on the data, on the taste data for the final network. And there is a bound again for two-layered nets with ReLU activations. Again, you have some failure probability 1 minus delta. Now it is for training data set initialization, and the bound looks as follows. So on the left is the expected risk of the data over loss of the final model, and it is bounded, upper bounded by the following. And
what is G here?
G is, again, it's a gram matrix, Gram-N of the kernel. Kernel computed
Which kernel?
Ntk.
Ntk?
The same, yes. And it says basically that if your data, your Ys, your targets are well aligned with the Ntk, so it means with G, with Gram-N, then the first term is small, because if it is well aligned, then this guy is small, because the spectrum of G minus 1 is 1 over spectrum of G. And that's why if your let's say your normal projections are large when eigenvalues are large, then your norms of projections are large for eigenvalues of the inverse kernel when the eigenvalues of inverse kernels are small. That's why for well-aligned Ntk, when Ntk is well aligned with the data, this guy, the first term is small. And yes, and this guy is called the complexity measure, and it is well correlated with actual loss. So we have L1 loss, which is green line, and we have this complexity measure, which is a blue line. Still, you have a vacuous bound because the complexity measure is at least 6 times larger than actual loss, and that's why this bound is still vacuous. But it tracks the actual loss well, and it's a good result. So we have the Ndk.
Excuse me, and how L1 loss was defined on CIFAR data?
I think it's a binary CIFAR. It's the first 2 classes of CIFAR. Not something like this.
Okay.
So what is the definition in Decay? It's an expectation of the kernel at the initialization over initial weights. How to compute it? First, of course, we can do Monte-Carlo, and it is applicable to any architecture, any model. Just take the expectation, that's all. Of course, it's noisy. And in some cases, in some simple cases, it can be computed analytically, in exact way. It is possible for RealU fully connected and convnets and without any modern stuff like Bayes norms, but still. And there is a comparison between CNNs without Bayes norms with RealUs and Cntk when we compute this kernel with different depths, and interesting insight that for small depths, Cntk outperform the CNN, but for deeper nets, this is not the case. And I don't know why for small depths, Ndk overperforms the real CNN, and for deeper nets, it's not the case. However, the obvious conclusion is that if we fix the kernel, performance gets worse, performance changes. And that's why the kernel evolution is important. And our approximation that the Ntk limit gives an approximation of the constant kernel. And it is not very, very correct, very precise, because we see that if we fix the kernel, then something changes. Hence, the kernel indeed evolves.
What is Cntk?
Cntk, we take a CNN architecture, then compute its expected initial kernel using some analytic formula, and then we just integrate our dynamics on the taste dataset.
And so for convnets without Bayes normalization, we can somehow get the explicit expression for the Ndk,
Yes,
right?
yes.
And how monsters they are? How do they look?
They look fine. They look not that monstrous. At least they are computable.
Okay.
At least there is a GitHub project, an official GitHub project of Google called Neural Tangents, that is able to compute and integrate the Ndk dynamics for simple nets without Bayes norms. I think this Ndk is just implemented in this library.
Okay, thank you.
Let us turn to another limit. Another limit model which differs conceptually from the Ntk limit. It's called the mean field limit. For now, consider a neural network with a single hidden layer. And note that for now, I have defined the network differently. I have introduced a factor of d to the minus 1 instead of 1 over the square root of d for the Ntk parametrization, and just 1 for default parametrization. That's important, this factor. And I have a training process. Again, I consider initializing my weights independently on weights. And in this case, I have this factors d to the minus 1, which comes from this factor in the definition of the model. That's why, again, I have weight increments that go to zero. Nevertheless, I don't want I don't want them to vanish. And for this reason, I rescale my learning rates. I scale my learning rates proportionally to d in order to overweight this d to the minus 1 factor. So I change my learning rates with widths. I make them proportional to the widths. In this case, weight increments do not go to zero, and weights evolve. Okay. Consider some strange objects called a weight space measure. Um, recall, we have D neurons, and we have an input weight and an output weight associated with each neuron. Let us associate um, an atom in the weight space measure to each neuron. So it's an atomic measure that sums to 1. We have D atoms. Each atom is associated with each neuron, and it's a measure in the space of output dimension plus input dimension. We can express the model in terms of this measure just by integrating by this measure. Also, we can express the training process in terms of this measure. So you can express the gradient descent dynamics in terms of the measure evolution. You have the initial measure, you have an evolution equation with some v. It's a kind of a gradient. It's a gradient at point AW. Some formalism. Almost nothing changed. We have just altered our side of view. Instead of looking at weights, we are looking at some measure in a weight space. And our weights now hidden inside this measure. So our measure encodes the weights.
Sorry, what is V?
V, you can perceive V as a joint gradient over A and W. You just compute. You assume that you have a weight AW, and you compute the weight increment. It's better say like this: a weight increment in this point.
So this is simply what you denoted earlier, previously as theta dot, right?
Right, almost.
Of our weight.
Note that the initial measure is random, because just recall that this measure has d atoms. Each atom corresponds to the weight associated with each neuron. Since weights are random, the measure itself is random. However, it converges to deterministic measure in the limit of infinite number of neurons. and the uh, limit measure is just a measure of a normal distribution.
Interesting. And why that happens?
It's quite intuitive. It just so a measure just imagine you are sampling points from standard Gaussian.
I can
And
imagine this. And I imagine that if the number of samples goes to infinity, then I converge to the normal distribution.
right.
You have a connected product. That seems a bit different thing.
No, it's not different because they are independent Gaussians, a product of a Kronecker product of independent Gaussians. You just it's a Gaussian
I
of
see. I see.
dimensionality 1 plus dx.
And why the dimensionality of A equals to 1?
Because I assume that I have a scalar network.
Power, right?
Mhm.
Okay, yeah. Then this is pretty obvious. Okay.
So the measure at the initialization converges to the deterministic one, and it gives the limit dynamics, which is the same, but we start with a deterministic measure.
Okay.
And this limit is called the Minfield limit, simply.
Which one?
Uh, this one. So you have a measure evolution, an evolution, a deterministic measure, and your output of network is defined in terms of the measure. Previously, it was defined in terms of this measure with d atoms. In a similar manner, we can define f infinity as the integral of the mu infinity measure,
Mm-hmm.
and it's the Minfield limit.
Interesting. So this
Uh,
is completely different limit from conceptual point of view. So we
yes.
keep neural network in a different way,
Mhm.
as a kind of taking expectations with respect to infinitely large number of neurons. And this is, I think, exactly what is written here.
Right, right.
But this holds true only for two-layer deep neural network.
Yes, I will discuss something about deeper ones, but this formalism is clear for two-layer nets. For deeper nets, it is much more complicated, but it's possible. What happens to the kernel in this limit? So we still uh, can define a kernel in a similar manner, and what happens to it? And it turns out that still, first of all, you have to define your kernel by, you have to introduce a factor of eta, which is learning into the kernel, which is fine. And this kind of rescaled kernel will still converge. Your kernel converges, but it evolves with time. It is not constant. So kind of in the Minfield limit, you still have, you can still express it at the involution of a model in the function space, driven by some kernel, which is finite, but this kernel evolves. Can we say about something about multilayer nets? First of all, it is completely not obvious, and I believe it is hardly possible, but I don't know for sure. That is, it's not obvious how to express a finite with dynamics in terms of the measure, and what should be the measure. Measure on what? It should be like measure on paths. But okay, still, a limit dynamics can be expressed as a measure of evolution. This kind of beautiful results because uh, some something decouples, and because of this decoupling, a measure of evolution is possible, and is a result of the last layer, the last year. And there is some problem. There is simple heuristic. I will not show you today, but there is simple heuristic that shows that if your nonlinearity phi is such that phi at 0 is 0, For example, if you have 10H or real U and your initialization is zero-centered, then a limit model vanishes if the number of hidden layers is at least 3. So kind of your mean-field limit doesn't make sense for deep enough nets. It makes sense for networks with 2 layers, with 3 layers, but with 3 or more hidden layers, it doesn't make sense.
That's interesting, and from the first sight seems quite strange and counterintuitive.
Maybe. It's just heuristic that um, um, that uh, that computes how fast what happens with your gradient with respect to weights at the initialization. And you can show that for deep enough nets, if you have at least 3 hidden layers, this gradient of the loss with respect to weights will go to 0. But if you have 2 hidden layers, it is not the case. A bit strange, but I don't have a slides here, but you can, I can explain your
So
some
again,
of the
phi
time.
is our nonlinearity, right? Phi is our nonlinearity of the neuron.
Phi is nonlinearity, right?
So in some sense, we transform some distributions on random variables with 0 mean. Okay. Anyway, I'm pretty sure that I will not be able to get intuition right now. So please continue.
Okay, so meaningful limit for multi-layerness is not that obvious. For Ntk, it was completely fine because Ntk was defined for any model, just any parametric model, and mean field is bounded in our structure of a neural network. That's why there are some peculiarities with deep nets. Open questions. I'm sure they're opened, but I may miss something. I haven't seen any non-asymptotic convergence guarantees. For example, something like if your network is wide enough, then it will converge to zero loss, to global minimum, given mean field parameterization. I haven't seen such things. Another thing that I haven't seen yet is generalization guarantees. So the mean field limit is much harder. That's why most people do Ndk, because it's much easier. And as I will show you later, if I will have enough time, the limit model that corresponds to the default parameterization resembles a mean field model. It's more like a mean field model than the Ndk model. That's why you have some discrepancy. People try to do something with Ndk, which is not realistic because our realisticness is more like mean field, and it's hard to do anything with mean field. Let's continue, and let's turn to a general treatment of networks in the limit of infinite widths. So consider a network with a single hidden layer. Yeah, a single hidden layer, and we initialize our network independently on the widths, and we introduce some general factor sigma at d, a general factor. And we already know that if we take sigma, which is inversely proportional to 1 over square root of d, and take learning rate to be constant, then we'll have Ndk limit if d is large enough. If we have sigma inversely proportional to 1 over d and learning rates proportional to d, then we'll have a meaningful limit. Questions, what happens to default parameterization? Do we have any other meaningful, well-defined limits in some sense with other scalings, for example? And which of them describe the finite with one best? I have already spoiler to you that the meaningful limit is a bit better, but still.
I'm sorry, may I ask a question, please?
Yes.
You said that mean field limit is closer to realistic scenario than Ntk limit. Could you please comment why? Because here we have d in the power minus 1/2. Here we have d in the power minus 1. So
I cannot completely explain why, but for now, but it is more realistic because in the mean field limit, your kernel evolves, and in the realistic nets it evolves too. That is why it's more realistic. There are some discrepancies. Okay. But again, it is true for nets with a single hidden layer. For deeper nets, there are problems with the manifold limit. Yeah.
And by realistic scenario, you mean like thin networks, not very, very wide networks?
For thin, they are quite wide, even for wide nets. For example, I would say 2 to the 9. 2 to the 9 would be almost midfield. And for 32, no, nothing. None of them will be a good proxy model.
Okay. Thank you.
Yeah, so let's be a bit of formalize. So we start with a model without any factors. And we have a training procedure, which is the following. We have a gradient step for output weights and for input weights, with eta A being a learning rate for the output layer and eta W a learning rate for the input layer, and learning and weights are initialized with zero-centered Gaussians with variances sigma A squared and sigma W squared. So yeah. What we do not like, this is standard definition. What we do not like here is that your weights are initialized with something that are generally dependent on D, on the weights. That is why we rescale our quantities in the following way. So weights are rescaled with the standard deviations on initializations, and learning rates are scaled in a different way, but it is done in order to so if you scale your quantities in such a way, then the model becomes as follows: by quantities with hat rescaled quantities. So I have rescaled everything. Without loss of generality, I can assume that sigma W, which is STD, which is an STD of the input weights, is equal to 1, because instead I can rescale my inputs. I do not have any assumptions on how do inputs behave. And the training procedure becomes as follows. So it's essentially still a gradient descent, but on some rescaled quantities. And in this case, your weights are initialized independently on widths. You see that this dynamics is driven by 3 hyperparameters. eta W and eta A, which are learning rates, and sigma, which is now, which was before STD of the initialization. Now it is a factor which is a scaling factor of the model. But before it was the STD of initialization. So 3 hyperparameters. 3 hyperparameters. And we assume that they obey power law dependencies with respect to D. As you remember before, for example, for mean field limit, sigma was inversely proportional to D, and learning rates were proportional to D. For Ndk, sigma was inversely proportional to the square root of D, and learning rates were constant. So we have covered both of the cases at least. And let Q sigma and QA and QW be corresponding exponents. Yeah. So what scalings are available? First of all, Ntk. Q sigma is minus 1 over 2, and both QA and QW are zeros. Mean field. Q sigma is minus 1, and both QA and QW are 1s. You have a, I would say, default scaling. You have a default parameterization. In this case, your initial non-scaled learning rates are constants. That is why scaled learning rates are the following. So A's learning rate is proportional to D, and W is proportional to 1. That's why you have the following. So the default parameterization is still covered by these formulas. And I will define one more, kind of a sim default. It's almost the same as default, but your learning rates are the same. They are kind of balanced. We shall see further. No, I think I have not this slide, but this sim default scaling will lead to almost the same model as for the default scaling, but it will be a bit more convenient formally. Let us now assume that exponents for both learning rates are the same, and I will denote it by Q with tilde. The question is, can we have a well-defined model, limit model, for other scalings different from Ntk and mean field? What if Q sigma and Q tilde are not the same as for Ntk and field? First of all, we have to define what is a well-defined limit model. Informally, I would say that the model is well-defined, the limit model is well-defined, if starting from some step k star, the model increment delta f d at step k is of the same order as the model output itself. It means that the change of logits, so the model output, let's say it is logit, is comparable to logit itself. So if the model is finite, then it should evolve in a finite way. If for some reason it is infinite, it is possible, but it can be fine still, because, for example, it is fine to have infinite logits if you have a cross entropy loss. So having infinite model, divergent model is fine because the gradients of the loss do not diverge, even for infinite logits. And in this case, I will try to, so I will require the following.
But
So
as far as I understand, if this our definition holds true, we cannot guarantee the existence of the limit.
Of the limit? Yes. So if you turn to classification, then what is, if you have a binary classification, then what matters is the sign. That's why your model can diverge, but the signs of the model may be meaningful still.
Well, that's true, but again, it doesn't follow from your definition. So from your definition, it still may happen that the signs will not converge when d goes to infinity.
Sign may not converge. A sign may not converge.
I would expect here the convergence of delta f over f, that it should converge to 0 when d converges to infinity, not to just some constant.
In what cases, if what is the case when delta f over f goes to 0?
Well, I would expect that this should be a definition of definiteness. That delta f over f should go to 0 when d goes to infinity. Then we can say that there clearly exists a kind of a limit model and a kind of a limit behavior.
But that means that your model kind of doesn't learn. It means that at step k, the model increment is negligible compared to the model itself. Hence, it just doesn't learn.
K is a step.
Yes.
So okay, then what happens if a model increment over model itself goes to some constant? But again, this doesn't, I think, tell us anything about the existence of the limit.
Does it tell us the existence limit? I think you're right, because so at least the limit can diverge, it can vanish, and my idea was that it is fine in many situations like classification. That's why I have introduced this definition. And but still, even in terms of science, something can happen, like alterating sign, so the sign may still be non-converging. Trying to think. Yes, I agree. That's maybe an issue, kind of, in this definition. Maybe something
and
more.
can we find something as false? The difference between the models trained with d and d plus 1 should be negligible in comparison with the output of the model trained with d neurons. Maybe we should define it as false. To assume that we have some training
and that means that the model, limit model, yeah, so it's a good definition. It says that kind of the limit in terms of d exists,
right?
But in terms of d, it exists. But does it mean? But it doesn't mean that the model learns or just says that the limit exists at any step k.
But well, I would say that this is in some sense more important, the existence of the limit, because only if the limit exists we can discuss the limit behavior and we can consider whether the model learns or learns lazily or learns conventionally. But in all cases, we should first be sure that the limit does exist when d goes to infinity. So maybe we need to establish several requirements here. One is existence of the limit when d goes to infinity, and another is the guarantee that model learns somehow.
Okay, I agree. I just said it should be elaborated more and have to think about this.
And Evgeny, one more question. How many slides do you have? Because we have already, well, the time of the seminar is already over. And I think that you still have some important material to discuss.
Yes, I think I will get just faster, maybe 5 minutes more or 10.
Are you sure? Maybe it's better to just to give you the opportunity of making another presentation.
I should say no.
Because I'm not sure how many slides remained, but it would be much better if we could discuss it in a quiet manner. So okay. If you believe that we have just few slides more, and we can discuss it, okay, then let's proceed.
Okay, I will. So yes, it's a definition of well-definiteness, and it turns out, so there is kind of a diagram. Recall that we have two hyperparameters, two exponents, q sigma, which drives the, which states how fast does sigma, how, which is this q sigma. You have q sigma and tilde q. And you have a phase diagram in the space of q sigma and tilde q. And each point in this diagram is a scaling of hyperparameters. And we can show that in this area, the model diverges with respect to itself. So it's a divergent case.
It actually explodes, right?
Explodes. In this case, it vanishes with respect to itself. And in this area, in this band, it's a well-definiteness band, where limit models do not, the increment of logis is comparable to logis itself.
And where is the default setting?
Default setting is not here because in default settings, Q alpha, QA, and QW are different, and we have assumed that they are the same in order to have a nice two-dimensional picture.
Okay.
But sim default, I will say it again, is almost the same as default, and it has the same. And yeah, and this point is mean field, this is sim default, and this is Ndk. And we shall show later that these three scalings are special in some sense. There are four properties that are the case for finite width networks and can be violated for limit ones. The first one is the limit model is initialization. A model at initialization is finite. For limit models, it can vanish or it can diverge. Again, we can define tangent kernels, and for finite width models, they are finite, and for limit models, they can vanish or they can diverge. And there are two other properties. And it will be good that if a limit model can satisfy all of these four properties of finite model at initialization, finite tangent kernels at initialization, and so on. And all of these four properties can be expressed in terms of the exponents. And each of the property corresponds to a line in this diagram. For example, this line corresponds to a property 1, finite logis at initialization. All of limit models, all of limit models that are defined, that are induced by scalings on this segment, have finite lodges at initializations. All of models, limit models that are induced by scalings on this dashed line have finite tangent kernels at initializations. And that's why we see that for Ntk, um, we have three properties because it is on the intersection of three lines. And for mean field and sim defaults, they have two good properties because they are in the intersection of two lines. And none of them are in the intersection of all four lines. However, these three models are kind of non-dominated because they are in the intersection of the maximal number of these lines. So they satisfy most of the properties compared to other limit models. That's why they're special. The interesting thing, and the other things we can show that, okay, these lines divide this band of well-defined limit models into regions. There are 13 regions. Some of them are two-dimensional, some of them are one-dimensional, and some of them are zero-dimensional. For example, the three special limit models are zero-dimensional regions in this band. And one can show that each region corresponds to a unique, distinct limit models. That's why we have 13 regions and 13 unique, distinct limit models that can be induced by scaling hyperparameters.
So that means that, say, all the models within the green triangle are in some sense equivalent.
Yes, sorry.
Pretty nice.
Mhm. It is possible to satisfy all of these four properties by modifying the model itself, the finite width model itself a bit. And we can modify the model itself in this way, just because in the mean field scaling, the only property that it violates is that at the initialization, the model vanishes at the initialization. However, we can correct it at the initialization by adding this term that that do not evolve, and it is not zero, and doesn't go to zero at the initialization. One can see that for, yeah, that's all. And the limit model for this particular network, kind of a network, will satisfy all of the four properties. And this limit model, I will call it initialization correct mean field. And we can test which of the limit model will be a better approximation for a finite width network. And we shall measure it by computing Kyle divergence between the lodges of the limit and the lodges of a finite width net. So we want to have the following: the lodges of the limit model will not diverge too much from the lodges of the finite width network. And that's a plot of the lodges of the Kyle divergence. So by x is a training step, by y-axis is a Kyle divergence. And we see that initialization corrected mean field keeps this Kyle divergence small, much smaller than for Ntk, because for Ntk it starts with a small Kyle divergence and then it diverges. Maybe because the kernel evolves. And for mean field, it starts with high Kyle divergence because it starts with a zero model, essentially. And Yeah, and I have promised you to show how what happens to the default parameterization. So we already know that the Ntk limit leads to a dynamics in a function space driven by some constant kernel, constant deterministic kernel. In the mean-field limit, the limit dynamics is a deterministic dynamics in some measure space, conceptually different. For sim default limit, you still have a deterministic dynamics in the measure space, but a bit different one, but still a deterministic dynamics in the measure space. And for default limits, it's almost the same. And I will not show you what the dynamics looks like, because that's too much. So takeaways. First, we can consider an infinite width limit as a proxy model for a finite width network. There are good optimization translation guarantees for the Ndk limit. The Ndk can be computed exactly for simple deep networks. Mean field and Ndk limits are not the only possible. However, there are a finite number of possible infinite limits that in some definition are well defined, but the definition is questionable, maybe not a good definition at all. The Ndk limit is not a perfect proxy for a finite width network, and we can come up with a bit better proxy, but only for a shallow network, because I have, in the last part of my presentation, I have discussed only shallow nets. And for deep nets, everything is much harder just because we had problems with mean field limit, and we should have the same problems with any limit that is expressed as an evolution of the measure, because the problems, the root of the problems is the measure. That's, I'm all.
Okay, thanks a lot for this fundamental talk. Do I understand right that Ntk is the only limit which can be explored beyond the two-layered deep neural networks, at least up to now?
Seems like can be explored. No, the mean field limit can be explored for 3 layers, and even for more than 3 layers if, for example, you have sigmoid nonlinearity. If you have, for example, an H, then it will vanish, but it's some heuristic. Well, according to the heuristic, it is the case. What do you mean by explored? Do you mean having some guarantees or something like this?
Well, I mean, you have something that doesn't vanish.
Something doesn't vanish. You can have something that doesn't vanish.
Okay, yeah, I got it. So, do I understand right that the last part was your result?
Yes.
So this was the ISML paper this year.
No, the ISML paper, I almost haven't covered the ISML paper because the ISML paper was about...
Evgeny, just yes or no? So,
no, it was about submission of SLR.
Okay. But anyway, I think if there could be a man who could teach fundamentals of theoretical fundamentals of deep learning, this is definitely you, at least in our country. So, colleagues, any questions? I think that the most of the questions have been already asked during the talk. And I think that we'll all have well to return to it again and again, especially those of us who are exploring well some limits behavior of deep ensembles and of wide neural networks. We probably your talk is could be a source of intuition for us. So thanks again.
And thank you for your questions, and thank you for having to giving me an opportunity to give a talk. It's a pleasure.
Oh, you're always welcome. And colleagues, so next week we'll have a scientific popular seminar with our special guest Vladimir Surdin, who is a leading researcher in one of Russian astronomical institutes, and also is pretty good in popularizing astronomy and astrophysics. So we'll have a Q&A session. So please, those of you who would like to ask any questions to him, please send me or Ekaterina your questions, because the priority will be given to the questions which were sent in advance. And only if we have time, I'm allowed to ask questions which haven't been sent before. So please do not hesitate to do it. Otherwise, we have a risk that the only questions which will be asked will be mine, because I already have got quite a lot of questions which I'm interested about, but I also would like to give you an opportunity to ask him as well. So that's all. See you next week. So cheers.